Alright, so in preparation for a more serious discussion of Ekin layers, I want to review a mathematical theory called boundary layer methods and something called perturbation methods in general. I say review, but it's probably not review for most of you. Maybe this is the first time you see it, and so I think it will be a useful lecture to help you think about equations and how we go about thinking about equations that we cannot solve. So most of the equations that we see in our system science and physical oceanography and mathematical physics in general are equations that we can't solve. So in the textbooks, we always come up with simple models that can be solved exactly so we can focus on the physics. But in practice, especially in fluid mechanics, we almost always have problems where we cannot solve them exactly. And so that leads to either these complicated general circulation models or climate models, which then are as complicated almost as the real Earth system to understand, or very idealized models that are so simple that maybe it's hard to see if they contain the relevant physics. And so boundary layer methods is a way to come up with a hierarchy of equations that we can solve and that might help us learn about the physics that we care about. Anyways, now we're just going to do a math problem, and I'm going to put down an equation. Let's say we want to solve this equation, y squared plus epsilon y equals 1. And we're going to imagine where epsilon is a very small parameter, much less than 1, so it's a tiny parameter. So we know how to find the general solution of this. We can just plug it into the quadratic formula, and we're going to get the answer that we want. We're going to get both roots. But suppose we don't know the quadratic formula, right? So that's the case we want to think about. Because in general, we're going to get equations where we don't know how to solve them, and we want a general method. So pretend we don't know the solution to this thing. When we stare at this for a while, we might imagine, well, if epsilon is small, then y squared should be close to 1, and that means that the true roots are going to be y is plus or minus 1, right? There's going to be a root at plus 1, a root at minus 1, roughly. And then there's going to be some corrections that we need to think about because they're not exactly plus or minus 1. And so if we now think of this as a y, so maybe one way forward is to think of y as a function of epsilon, right? So we can try to find the general solution where y is a function of epsilon. And so that would give us y of epsilon. And then we don't know what that function is. Maybe we could try a Taylor series, and that would be y of 0 plus y primed evaluated epsilon equals 0 times epsilon plus 1 over 2 factorial y double primed evaluated epsilon equals 0 times epsilon squared plus 1 over 3 factorial y triple primed at epsilon equals 0 epsilon cubed plus dot dot dot. So maybe you would think doing a Taylor series, we've used that a few times in the course, maybe that's the way forward. But very quickly we think, well, sure, if we do the quadratic formula, we can plug in the solution, which we get from the quadratic formula in terms of epsilon, and take the first, second, and third derivatives and plug it in, and we get our Taylor series. But that's not very useful if we don't know the quadratic formula, which is the case we're considering. However, if we look at the form of the Taylor series, we realize that these coefficients here, the y prime evaluated epsilon, that's just going to be some constant, right? And same thing, this will be some constant, and this will be some constant multiplied by epsilon cubed, constant multiplied by epsilon squared, constant multiplied by epsilon. And so maybe instead of trying the general Taylor series, maybe we could look for a solution of this form. Y is equal to y naught, some constant y naught, plus some other constant y1 times epsilon, plus y2 times epsilon squared, plus y3 times epsilon cubed, plus, and so on. And then we could imagine substituting this in the equation to see if we can make any progress. So let's do that. So if I plug this into the equation, what I will get is y naught plus y1 times epsilon plus y2 times epsilon squared plus dot 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 all squared plus epsilon times, and then I plug in this in there, y naught plus epsilon y1 minus 1 equals 0. And I get this equation. right? And it's got an infinite number of terms. But now I could try to collect all the terms together that have the same powers of epsilon. So we can rearrange the terms in the following way. So from the first one, terms that involve epsilon to the power 0, I'll get y naught squared. There's no other terms that will have a power of epsilon to the 0. In this one, there will be none, right? They all have at least a power of epsilon, and then there will be minus 1 times epsilon to the power 0, which is just 1, plus. And now we're going to collect all the terms in power that are that multiply powers of epsilon to the power, or epsilon to the power 1, sorry. And so in this case, we will have y2, y naught, y1, right? 2, y naught, y1. That will have 1 epsilon in it. Right? This is a square term. And then in this case, we will have plus y naught, right? This is the only one that will have a power of epsilon. The other terms will have power epsilon squared, epsilon cubed, and so on. And then the last one, of course, is gone already. It has no powers of epsilon. Times epsilon to the power 1. And then we can do the same thing for the powers of epsilon squared. And what we get is, from the first term, we'll get y naught times y2. So we'll get 2 y naught y2. That'll give us an epsilon to the power 2. And then there will be this one squared, plus y1 squared. And in this one, we'll have plus y1 times epsilon squared, plus dot 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 equals 0. And we could keep going, doing the same thing to the powers of epsilon cubed and so on. And now this equation here, right, is going to be valid provided epsilon is small, right? But that's the only real condition we have, is that as long as epsilon is sufficiently small, then this power series should converge, and we should be able to solve for it. But epsilon is still an arbitrary parameter. It could be anything. So clearly, this term here, as epsilon goes to 0, this term will go to 0 faster than this one. This one doesn't depend on epsilon, whereas this one is going to 0 as I let epsilon go to 0. And this one's going to 0 even faster, and the next one's even faster, right? Because they're in higher and higher powers of epsilon. So the only way that equation could be true in general is if the first coefficient equals 0, the term that multiplies, the coefficient that multiplies epsilon to the power of 0. So that means that from the epsilon to the 0 term, I know that y naught squared minus 1 equals 0, which means that y naught, is equal to plus or minus 1. Now, if this one vanished, then this one has to vanish because it's going to 0 faster than this one, right? This one is epsilon, this one's epsilon squared, and if this one has already vanished, then this one must vanish on its own. So from the epsilon 1 term, I get 2 y naught y1 plus y naught equals 0. And we already know what y naught is, right? But anyways, y naught cancels. I can cancel y naught. And then y1 is equal to minus 1/2. Right? And then I can go to the next term, which it must vanish, because epsilon is going 0 to 0 faster than all the other ones, so this coefficient has to vanish. And what I'm left with from that one is 2 y naught y2 plus y1 squared plus y1 equals 0. And now I know what y naught is, I know what y1 is, and so I have a linear equation in y naught, which I can solve. So this gives me minus y naught. If I plug in the I plug in y naught, which is plus or minus 2. So I have plus or minus 2 y naught, no, y2. That's 2 y naught, y2. Plus or minus 2 y naught, y2 from the first one, plus y1 squared, which is plus 1/4, minus 1/2 equals 0. And from there I can solve for y2, which is equal to, this will be 2 over 4 minus 1 over 4 will be 1/4, so plus or minus 1/8. And so then now I have a form of the solution. If I can erase all this stuff here. And I could keep going, right? You can then equate the powers of epsilon cubed and so on. I'm running out of board space, so I will stop. But what I get is y is equal to plus or minus 1 minus a half epsilon plus or minus 1 over 8 times epsilon squared plus dot dot dot. And since epsilon is a small parameter, I can truncate. I can truncate here, and I get the original solution plus or minus 1, but I get the first order correction in a power of epsilon, and I could keep going if I want more precision. Keep the next term. Now I have a solution that is accurate up to order epsilon squared, and in principle you can keep going to whatever accuracy you like. Alright, so this was a nice, simple perturbation problem. I'm telling you the mechanics of how we go about solving these problems. Now let's think of a slightly different problem to see where some complications can arise.